Okay, welcome to our first video series on this channel, and this video will be taking you through mean compare. Mean compare is a principle that we use in data analysis to be able to determine if there exist differences between groups in our data. So in this approach, we would basically want to ensure that you should be able to find out if there is a mean difference. We compare means for different scenarios, and for now, in this series will take on 4 different scenarios. The first, we'll look at the one sample t-test, which will be a focus of today's class and today's lecture video. We'll move on to the independent sample t-test. We'll get to the paired sample t-test, and from there we'll move on to ANOVA. So that having said, this will help us to be able to make inferences if there exists statistical difference in our groups. Now, the one sample t-test is used when you want to compare the mean between one data set and a specific constant. Put simply, you want to compare the mean of your data and the mean of a known population. And a good example could be that you want to check the performance of a school with respect to national performance of all the schools. You know the average of the national average for the schools, and you want to compare if the average from your school in particular or any other setting is different. And the independent sample t-test is used when we have 2 groups that are unrelated, and so we want to see if actually there also exists statistical difference between the 2 groups, their means. In this case, remember we're talking about means. Now for the paired test, this is used when we want to compare the groups of 2 variables that are related. This is highly utilized when we have pre-test and post-test scenarios, when we have control and experimental scenarios where we go with the independent sample t-test, but for pre and post-test we go with the paired test. And ANOVA comes in when we have more than 2 groups. If we have more than 2 groups for independent samples, then we will use ANOVA. So let's get started with our first, which is the one sample t-test. Now the approach I will use in this lecture is that I will explain to you what the one sample t-test is all about, where the assumptions behind it, and I will go further to take on a practical example using SPSS and how you interpret your results. So that is the approach that we will use for this class and for this lecture. Now let's start with the one sample t-test. As mentioned earlier, we said that the one sample t-test is used when the researcher simply wants to determine if there exists a statistical difference between the sample data set and a hypothetical or a known population mean. This population must always be known, but sometimes we hypothesize the situation. For example, you may want to show that a new teaching method for people struggling to learn English grammar can improve their skills to the national average. So we have the national average, and you are introducing your teaching method so that we see how this teaching method from your data or from the particular school will affect the overall scores of students. So the next, we talk about the assumptions. Principally, there are about 4 assumptions that you will need to test before you analyze your data using the one sample t-test. Assumption number 1, your first assumption must be that your dependent variable should be measured at an interval or ratio scale. In other words, we are saying that your dependent variable, the outcome variable, must be continuous. Now, if you don't have an understanding of levels of measurement, I will recommend you go and look up while you research or you check any of our videos. We have a video on levels of measurement to understand what we mean by levels of measurement. Now, the levels of measurement helps you to choose which statistical tool to use. So it's one important thing for a statistician or a data analyst to know the levels of measurement. Now, put in our case, since we are talking about this, we may have exams marks. We may want to look at the revision time where we measured in hours. We want to see if students have been studying. We may want to measure IQ, maybe from 0 to 100. We want to measure weight in kilograms. And so if we do this, it gives us a dependent variable that is continuous. The next assumption is with respect to the independent variable. Now, your independent variable must not, be correlated or related, which means there is no relationship between the observations. One variable should not appear in the other. It means they should be dependent. They should be different. Now, the assumption number 3 is that there should be no significant outliers. The principle of outliers in statistics talks about extremely large or small values. These are values that deviate from the pattern when we want to talk about outliers. For instance, if you are looking at performance of students in class and you discover that the average of the class is 11 on 20, there are students with 12 on 20, 13 on 20, 8 on 20, 9 on 20, and there is a student with 20 on 20, then the student with 20 on 20, there's a possibility that the student will be an outlier because the student will make the class to seem to be performing far more than the reality, right? Or maybe a student with 1. So those are extremely large or small values that will affect your test. Now, the fourth assumption is that your dependent variable should be normally distributed. This is a parametric tool. The one sample t-test is a parametric tool. So we talk about the normality as a central and a critical element when you are dealing with parametric analysis. So your dependent variable must be normally distributed. And SPSS offers you different ways to test for normality. We can test for normality using the Shapiro-Wilk test for normality. And we can test for outliers using the Mahler-Nibbles test. And so which looks about the distance. So those are the 4 principal assumptions you need to evaluate before you consider running the one sample t-test. Now, we have said in order for us to do this, I have an example here. The data set is provided by SPSS, and the essence of the data is to allow us to examine. So we want to do a practical example so that you should be able to do it on your own. So we said test the difference between a sample mean and a known or hypothesized value. It allows you to specify the level of confidence for the difference and produces a descriptive table for each test variable. Now, this is our example. A manufacturer of high-performance automobiles produces disc brakes that must measure 322 millimeters in diameter, right? A quality control randomly selects 16 discs made by each of the 8 machines. The machines are 8 of them. Note this. We have 8 machines, and we have 16 from each machine, which means 16 forms our N, and the number of machines is 8. You need to be understanding to understand this. Use the one sample t-test to determine whether or not the mean median of the breaks in the each sample significantly differs from this value. This is our hypothesized value. This is our population mean, the known mean that we want to test. Now, keys to take. A nominal variable machine number identifies a production machine used to make the break. Because the data from each machine must be tested as a separate sample, we must split this data. Now, this is based on the SPSS data that we have, that they provided for us. And so I will show you how to do that. But before that, how do we run this out? You have to go to data, take split. This dialog box opens. You take the variables. Now, the dialog box opens, you have machine number, we have these breaks, and since we want to share or split our data by groups, we take groups compare, and we take on continuous. Once we do that, we come back now to analyze, go to compare means, take one sample t-test, and you run, you have this output, right? Now, this is our output. Now, with this output, we can go ahead and do the interpretation. The first is the table, the output table that gives us our one sample statistics. Now, the one sample statistics gives us our number of machines, which say the machines are 8 of them, machine 1 up to 8. We have our n. So we said each machine we took 16 samples. This is our 16, which is our n. So the mean for the 16 machines for machine 1 is 321.9915. This is the standard deviation, right? Looking at this, we cannot say if it differs from the 322 that we are expecting, right? We have machine 2, the same situation. Now, the next table gives us actually our test statistics, the one sample t-test, and we are able to see here that they give us the machines and their t values, the degree of freedom. This is n-1 gives us 16, degree of freedom, since we have one variable, right? So we have our seek. This seek value provided by SPSS actually represents what? The p-value, the probability value. We have our mean difference. We have the 95% confidence interval that gives us the lower bound and the upper bound, right? Now, as we want to go deeper, I want to ensure that you understand some key things. With SPSS output, there's a possibility for you to conclude whether your test is significant or not using 3 possible options. We use 3 possible options. The first option is using the t-test, which is the test value, right? Now, once you're using the t-test, you'll look at your calculated value and compare it with the value of the table value. We have the t-table, the table value, so you need to know about the t-distribution table. So we have the degree of freedom. Once you take the degree of freedom, you compare your calculated value with the table value at this degree of freedom, and if your calculated value is less than the table value, then your test is insignificant. But if your degree of freedom and the test value is greater than, your degree of freedom gives you the t calculated to be greater than the table value, then your test is significant. That is one way. The second thing is to use the p-value, which is the probability value, p-value. This p-value is your probability value. Now, this p-value, which is this value here, if you are testing at 5% significant level, the rule says that once you convert this, I'm giving you a simple way to do that, right? Yes, if you are testing at 5%, it means you are testing at 0.05, right? 0.05. So if your value calculated is greater than this, it means your test is insignificant. So by now you should be able to say whether you have tests here that the first machine significantly differs from our 32 or not. I'm sure you should be able to say that. right? Okay, that is the first thing we need to be able to do. Now the second thing is that, still looking at this, if on the other hand or the opposite, your value that you have here is greater than this, is less than this, then the test is what? Significant. If the value you have is greater than, then the test is significant. And so that's why we see here that this one is insignificant, because the value here is greater than this. Now if you check with machine 2, which is the second machine, you discover that this is significant. And what this means is that our calculated value, our machine, what this machine, particular machine, the second machine is giving, differs with our expectation to a great extent. So we cannot use this machine. This machine cannot give us our expected results. It will not be an ideal tool for us to use. And the last part is using the upper and the lower limit. This, if you are dealing with this test and the lower limit is negative, the upper part is positive, then your test is insignificant. If it is positive, the test is significant. And negative, the test is significant. That's why you can say this is negative and this is positive. This is positive. Some other people explain it by saying that if your value crosses 0, then your test is insignificant. If it doesn't, it means it is insignificant. That there should be no inclusion. Remember, there are some other statistical analysis that will not use base 0, they will use 1 to draw their conclusion. For instance, logistic regression. I just want to indicate that, right? So basically, that is what you see. So if you want to conclude based on this, we will see that we should retain machine 1 because it is insignificant, retain machine 2 because it's insignificant, retain machine 3, we reject machine 4, we retain machine 5, we retain machine 6, we reject 7. Excuse me, let me delete this, sorry. Yes, we return the 8th machine, right? So how many machines are we expected to retain because they are giving us expected results? 1, 2, 3, 4, 5. And so machine 7, machine 2 is not good for us. So does 4 and the 7th machine. So that is how we saw it for this section. And so just as a quick review, we say that the T column displays the observed T statistics for each sample, calculated as a ratio of the mean difference divided by the standard error. The degree of freedom helps us to know the number of cases, and is equal to n-1. We have the column, which is 15 degree of freedom. The mean difference for the machine is obtained, and we calculate with our 95% confidence interval. So thank you, and we show you now the practical example using data that we have. This is our data. Let's upload the data. You can find this data on your SPSS folder titled breaks. I'll give you the links at the end of this data. You'll find the description. So this is our data. Now this data, I will need to split the data, and we said to split the data, you come to data, split. I'll just have to reset this. And so since I'm splitting by the number of machines I want to compare, I take compare and I put this, I take OK. My data has been split, and I need now to go to analyze, compare means, one sample t-test. I bring my test variable and I put the expected test level, which is 322. You go to this, we are testing at 95, it's okay, you take okay. And you have your results, same as we had explained in our previous lecture. So if you like the video, we recommend that you find the video interesting, you like it, subscribe to our channel so that you have, because we have a series of videos, we'll continue. We will come again to give you how to be able to calculate the one sample t-test. We see the pair t-test ANOVA in this series of videos. Thank you, and see you in our next video.